This exercise asks us to evaluate the line integral along C of cosh y dx plus x squared sinh y dy, where C is the rectangle with vertices 0, 0, 3, 0, 3, 5, and 0, 5. So let's first just sketch a really quick graph of what that looks like. 5, 3. So we have 0, 0, 3, 0, 3, 5, and 0, 5. And that is slightly misplaced. Let me just make that dot bigger. There we go. So C is this rectangle. Now we see on this integral sign, there's this little circle. This, recall from the textbook, indicates that we have a closed curve with positive orientation. And with a simple curve like this that encloses a simply connected region, that means that this is oriented counterclockwise. So we are traversing the curve C in this direction. Now, we could evaluate this line integral directly. We can easily parameterize each of the 4 line segments making this up. For each parameterization, we would get values for x and y and dx and dy that we can substitute in, evaluate, and work through this just like in section 16.2. But that's kind of a pain, right? It's not hard, but it's tedious and time-consuming. So instead, let's use Green's theorem, where if we label the interior region here as D, Green's theorem tells us that that line integral of something of the form p dx plus q dy is equal to the double integral over that enclosed region D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. All right? So if we take this original integral up here, and let's call that I, now we can say that I is equal to, so the form that we have is in that p dx plus q dy form. So we can now apply Green's theorem here and say that this will be the double integral over D of the partial derivative by x of q, which represents the integrand attached to dy. So we have x squared times the hyperbolic sine of y minus the partial derivative with respect to y of p, meaning the integrand attached to dx, and that is the hyperbolic cosine of y. So we have all of that dA. Now looking what we have here, this might look briefly like a bit of a mess, but that's because I was just sort of directly plugging things in. Well, once we start working towards evaluation here, we see, okay, well, this region D is just a rectangle, so that can be easily expressed. I'll write the bounds later once I decide which order I want to put these in. If we take the partial of this with respect to x, so sinh y is constant, and we get 2x sinh y. We have minus the partial of this with respect to y, the derivative of cosh is sinh. So we have that. And looking at this thing here, we see this is common factor of sinh y. We could factor that out. That'll leave a 2x minus 1. So it doesn't really matter which order we integrate because this is separable. So let me just write dx dy because that's alphabetical. X goes from 0 to 3. Y goes from 0 to 5. So you see what I mean? This was a very easy integral to set up. And we're almost there, so let's just go ahead and finish simplifying this thing. We have the integral from 0 to 3 of again, if we factor out sinh y, we'll be left with 2x minus 1. And we can pull that out as a dx times the integral from, what do we have, 0 to 5 of sinh y dy. So we get, that looks like x squared minus x from 0 to 3 times the antiderivative of sinh is cosh. So we have cosh y from 0 to 5. This is 3 squared is 9 minus 3 minus 0 times cosh 5 minus cosh 0. So we have 9 minus 3 is 6 times cosh 5 minus cosh 0 is something that we can evaluate. And if you think through that carefully, that works out to be 1. And there we go. Oh, not cosine, hyperbolic cosine. I missed a letter when I was writing that. So 6 times the quantity of cosh 5 minus 1. This uses some relatively advanced theory, but especially if you have Green's theorem on hand to reference, it's fairly straightforward. You just sort of plug things in, evaluate, and that was a whole lot easier and a whole lot quicker than evaluating the line integral directly, which again, you could do here. It's fine. It's not hard. It's just tedious. You have these 4 individual line segments that you would have to parameterize separately and evaluate independently here and add all those up at the end. So this was a nice, quick little example of a case where Green's theorem can make things a whole lot simpler for us.